Hello and welcome back to Calculus 1, section 2.4, infinite limits. Meaning the answer is a type of infinity. Since we are on the one-dimensional domain, meaning x-axis, we are going to differentiate between negative infinity and positive infinity. They will be different things. There is a notion in 2D where those two infinities collide into a single point, and if you did that stereographic projection problem, I believe 52 or whatever the last problem was in the homework set for chapter 1 review, you ran into this problem, and if you thought about it, you would see how those two infinities collide into a point if you go to higher dimension. But since our line is one-dimensional, we have negative infinity on one end and positive infinity on the other end. That's for x-axis. For y-axis, which is also one-dimensional, we have the same notion of having positive infinity and negative infinity on opposite ends. Infinite limits refers to, I'm going to erase this one, so the title refers to answer is positive infinity or negative infinity. That's what it refers to when we say infinite limits. So the answer is one type of infinity. So essentially, what are we looking at? We are looking at a problem where the limit of f of x is going to produce plus minus infinity as x goes to certain finite value. The perfect example for this problem would be the limit of 1 over x squared as x goes to 0. The answer is positive infinity in this case. You can observe the graph for 1 over x squared, and you see that when you approach from the left, you get positive infinity. When you approach from the right, you get positive infinity. And that extremely important theorem from 2.2 says that when left limit and right limit give you the same value, the overall limit is that value. So now the left limit, approach from the left, gives us positive infinity. The right one gives us positive infinity. Therefore, overall limit is positive infinity. We also have situations where the limit does not exist, like for 1 over x. And the reason for that one, right, would be that the limit for the left is negative infinity and the limit from the right is positive infinity. Again, you are looking at the function and where it goes as x approaches a value. So you are looking at y values. What do y values do as you approach? So you see that as you travel on this line, right, as you travel on this line, the y values shoot to negative infinity. As you travel on the other line, they approach positive infinity. So this one does not exist because limit 1 over x, x approaches 0 minus from the left is negative infinity, and limit 1 over x as x goes to 0 plus is positive infinity. They do not agree, therefore the limit does not exist. So all of these examples are examples where we have what we call infinite limits. So essentially we are looking for a situation where the answer is positive infinity, negative infinity, or one-sided limits give us positive or negative infinity. The overall limit might give us, does not exist, as we can see in this case here. So for infinite limits, we have an extremely important mathematical concept attached to limits at infinity. You did the class prep, so what is that concept? No, that's the next section. That's 2.5. What is the concept for infinite limits? Yes, which one? The vertical, yes. So the most important aspect of this would be the vertical asymptote. Vertical asymptote. That is the most important concept. What do we have for this vertical asymptote here? Well, vertical asymptote is that vertical line that the function cannot cross. And that vertical line also is a break in the domain of the function. So it's extremely important. The vertical asymptote was defined in your pre-calculus class, but it was defined loosely, and you memorized that you set denominator equal to 0, and you get it, which worked well in pre-calculus, but that is not going to fly in calculus. So we have a different definition for vertical asymptote. And you need to know this definition because now you are learning more powerful techniques. And we'll see how the difference than pre-calc stuff you learned so far. So if the limit x approaches a minus of f of x is equal to plus minus infinity, or limit x approaches a plus of f of x is equal to plus minus infinity, then we have vertical asymptote at x equals a. This is your definition, let's say, of vertical asymptote. So if any of the one-sided limits go to any of the infinities, you have a vertical asymptote there. Note that this definition doesn't say anything about the overall limit a. It's one-sided limits. We also know that one-sided limits always produce a result. They are never does not exist, right? One-sided limits always give us either a value or infinity. You will never have d and e on a one-sided limit. So now you can look at the function f of x equal 1 over x and quickly claim that the limit x approaches 0 minus of 1 over x is negative infinity, which implies vertical asymptote at x equals 0. This is the proper way to do a problem that involves vertical asymptotes in calculus. You have to do the limit. Asymptotes are defined through limits. So now we're defining a vertical asymptote, and the vertical asymptote is the simple limit calculation, one-sided limit, and if you get the infinity, you have the answer there. Now, I will go back now to pre-calculus course and ask. So x minus 4 over x squared minus 16. What's happening with our asymptotes? Yes?
It's getting smaller and smaller.
No, I'm asking the asymptote situation. Right? What is the... Do we have any asymptotes? If so, how many? And all of that stuff. Okay. So? Yeah, I'm asking where the asymptote or asymptotes are. Yes. Negative 4 and positive 4. How did you get that?
We're solving for denominator. Yeah.
Denominator. So see, in pre-calculus you learned that you are supposed to set denominator to 0, and that's where the asymptotes are. Calculus, what you said, is going to fix that, actually. So now we have to fix that statement. That statement is not mathematically correct because it doesn't give the whole picture. So, if this was anything but x minus 4, you'd be correct. However, x minus 4 actually cancels, and the positive 4 is not an asymptote. Now, I'm going to use calculus to prove that. So this is what we're going to do. We are going to set denominator to 0. But that will not necessarily give us asymptotes. That is going to give us all candidates for asymptotes. And then you have to check each one of those candidates in the limit, and whichever one gives you infinity is the asymptote. The other ones will not give you infinity. Those are not asymptotes. So now, x squared minus 16 equals 0 produces plus and minus 4. Plus and minus 4 are candidates where asymptotes could occur. Well, let's check positive 4. The way we check positive 4 is limit x approaches 4 plus or minus from the left. Let's do minus from the left. And we have x minus 4 over x squared minus 16. We learned in the last section that these problems are solved by factoring. So x minus 4, x minus 4, x plus 4. And as you can see, you are not getting infinity. You are getting 1 over 8. So, not an infinity, so no VA. No VA. So what do we actually have there? What we have is the open circle in the graph. It's just a hole. And actually, if you graph this function on the calculator and you zoom in at x equals to 4, you will see a missing pixel. If you go to the table feature, it will say error. But it says error for asymptote as well, so table feature is not really helpful to actually see that. Now let's see what happens if we try to use negative 4. So how about limit x approaches negative 4 from the left of x minus 4 over x squared minus 16? Method of calculation is the same. You still have to factor the same way you did before, except now, once you cancel, you are still getting 0 in the denominator. So now you are not allowed to plug in because it doesn't work. X goes to negative 4 minus. You see, now you can't plug in because you get 1 over 0. And you have to resort to graph or a chart. Now, luckily, this is an easy function. It's 1 over x plus 4. What is this plus 4? What does it do? The plus 4. What is the plus 4? How do I graph this? Yes?
Maybe +4 shifted 4 left.
Very good, +4. It's +4 directly on x, which means shifts to the left 4 units. So the graph for this is going to look exactly like 1 over x, except it's shifted, it's shifted, and it goes through the 4. Now, first of all, on the graph you see there is a vertical asymptote. Sorry, shifted to the left. Guys, pay attention. Fix my silly mistakes faster. Okay, I picked Saturday class because I know how much you love weekends and how enthusiastic you are during weekends and so on. So let's have that energy, you know, feed into this process of or I promise you I'll retaliate. It's very simple. Starting next class, PowerPoints and me talking like this. Good luck with 5 hours of that. Maybe we should try once. Just one 5-hour period of PowerPoints and me going 4 limit and x.
Did I have subtitles to the video for that episode?
There will be no stream, there will be no lectures, there will be just, I'm not writing anything, I have PowerPoints, why would I write? Right, everything is displayed. And we also turn off the lights, obviously, because you see better, you see screen much better. We'll put the blinds down, it's going to be awesome. Or you double up on coffee in the morning, I want to see you jumping up and down on your seats and twitching but doing math. That's what I need. All right, so what is happening as we are approaching from the left? We clearly see that this limit is equal to -infinity. In our definition for vertical asymptote, we are looking for one type of infinity, right? And we got it. So that means yes, we have VA at x equals -4. Oh, and please just don't trigger my allergies by writing VA equals. This has no meaning in mathematics. This means nothing. This means nothing. Don't write it. All right. We have the vertical asymptote at x equals -4. X equals -4 is a mathematical equation. VA equals -4 has no meaning. It's not defined as anything. So just don't waste your energy to write it. Write the stuff properly. So let's recap the entire problem. We are looking at the PreCalculus1 problem here on the cloud that has x minus 4 over x squared minus 16. What you learned in your previous life was that setting denominator equal to 0 gives you vertical asymptotes. We have to correct that now and say it gives you the candidates for asymptotes. This was a perfect example where you've seen that one of the candidates is not vertical asymptote and the other one is. You can have this situation where none of the candidates are asymptotes, or one of them is, or both of them are, or maybe you have 7 and they all are. Tangent function has infinitely many asymptotes. You need to also have that concept in your head. Yes, we do draw just a principal period of tangent, which looks like x cubed, and we put 2 asymptotes on sides. But you have to understand that tangent is periodic function, like every other trig function, and it will have infinitely many asymptotes, vertical asymptotes. So we can have no vertical asymptotes. We can have 1, 2, 3, or infinity, right? We can have any number of vertical asymptotes. It depends on function, right? Depends on function. Other trig functions that have infinitely many asymptotes are secant, cosecant, tangent, and cotangent, right? So 4 of them have infinitely many vertical asymptotes, where sines and cosines do not have vertical asymptotes at all. Exponential function does not have a vertical asymptote. It has horizontal, right? But then the logarithmic function does at 0. We've seen that 1 over x squared, and then 1 over x to whatever power will have a vertical asymptote at 0. Your job is not to memorize this case by case. If you learn this, right, the red statement, you don't have to know case by case. There are upward of 2,000, 2,500 functions in the world. We cover in our calculus courses and PreCalc courses maybe 10 of those, right? So, yeah, for 10 of those, you might as well memorize which function has which asymptote and where. But then you remember that that's not even a drop in a sea of what is out there. So learning the principle will allow you to find those vertical asymptotes. Now, vertical asymptotes are extremely important in your design, which companies like Sony and Samsung are yet to work on. Remember the question from last class where we talked briefly about creating a mini explosion in the outlet? It's the experiment that it's very easy to do. With the isolated piece of a wire, done, right? And then you go reset the switch. That is the vertical asymptote. What happens at the vertical asymptote is that the y value is trying to be infinity. Now, whether it's a positive infinity or negative infinity, that's just our perception of it. The key is that it's trying to be infinity. And I remember writing that stuff last time where I said that if you have 110 volts in the outlet and you're dividing that by resistance, where the limit of the resistance is trying to go to 0 because you are shorting it, you are getting positive infinity. Current is trying to go to positive infinity. Current is proportional to temperature. Temperature is trying to go to positive infinity. We have the buildup of infinite energy in small interval of time. That translates into the motion, right? So, when you are dealing with application, let's say you want to be engineers, and I'll explain the word want to. You will be designing batteries or storage devices or whatever, bridges and so on. Any type of infinity in those cases is bad, because you don't deal in engineering with infinite mass, infinite time, infinite energy, infinite anything. Everything that you see and touch and build is finite. You have the battery that produces the finite voltage, which is distributed over the circuits with a smaller voltage, over the voltage drops and so on. There are no infinities that arise in any of those designs. When you solve a differential equation, wait for Calc1 too, right? You solve differential equation to get the mathematical model which models something. You take the limit, and if that limit ends up being infinite, the model is garbage, and what you are making is going to fail, explode, or something. You have to be very careful about those things. So as much as this could look abstract and the vertical asymptote and all of these kind of things, remember, all of this is the base for physics. Physics is base of engineering. You are still in step 1 talking about the asymptote, which is abstraction, which is translated later into concrete physical principle that through engineering you can touch and build and mold into something that we can use. So when you approach this course, which is the base for all of that, try to look for that applied meaning for everything we do, every single concept. Because this is the course that drives differential equations, which drives all of physics, which drives 100% of your engineering. So yes, you are not going to integrate once you become engineers. But this concept here, as electrical engineer, is rule 0. And that is, do not have infinity anywhere. And you detect that with the limit. Now, clearly, that by that time, when you are engineer designing circuits and so on, let's say electrical, do we have electrical engineers? Wannabe? All right, one. Designing circuits, right? You will spot an equation when the denominator is trying to be 0 and so on, because you've dealt with enough mathematics in your field, electrical engineering. About 75% of your education is math, for a reason. But then that math becomes more of a kind of graph, quick, shortcut kind of method, right? Like proofs and stuff like that. So, yes, you can pass the class, sure, but then that exactly will going to distinguish those engineers that work at these high-profile places and engineers that do not work in a high-profile places. It's the knowledge that separates right, the skill that you guys develop. And it starts with this. So now what we're going to do is take a look at one or two additional exercises, and this is done. That's all 2.4 is. A vertical asymptote. So let's see.
Quick question about that last one. Since they go in separate directions, an overall limit would not exist?
That's true, but we don't care.
Okay.
Because the vertical asymptote requires for one of the one-sided limits to be infinity. You also have functions like e to the x that would have only one-sided, ln x, that would have only one-sided approach to consider. So if you are considering f of x equal ln x, let's say, you look at the graph going through 1, and you see that the only thing that you can consider is the limit x approaches 0 plus of ln x, which turns out to be negative infinity, implying VA at x equals 0. So there's nothing on this side to test the left approach. So we are not concerned for asymptotes with the overall limit. The definition never mentions overall limit. The definition clearly states if one or the other is infinite, boom, vertical asymptote. If they're finite, no vertical asymptote. You get the open circle. You just get the hole on that spot. So technically, the graph is going to look like this. That's how graph looks like for that function. You have a vertical asymptote at -4, and you have the open circle at 4, which is, and this circle has the coordinates 4, 1 over 8. That point doesn't exist. It's whole. If it existed, it would be 4, 1, 8. So that's the location in space, 4, 1, 8. But the function doesn't exist at that point. The calculator is going to return error. But see, the calculator can only compute one value at a time. Calculator doesn't understand the difference between function value does not exist and the vertical asymptote. Yeah.
So how do you know when you're solving and you get 1 over something that will equal 0, and that could either be a vertical asymptote or you solve it wrong. Like, you need to do it a different way. So how do you
No, just don't solve it wrong. That's the shortest answer. But these are the two possibilities. The possibility is to get a finite value, which is not infinity, which is open circle, or get one of the infinities, which spells out vertical asymptote.
Don't you get 0 in the denominator for that one?
Yeah.
But with what we were doing before, when you get 0 in the denominator, you have to solve it a different way.
Oh, you mean how to solve this, regardless of the concept of the asymptote?
Yeah.
Ah, when algebraic methods fail, in which case they do because there is nothing in factoring or rationalizing you can employ, your last resort are chart and graph. I use graph. We cannot solve everything in mathematics using algebra. So, like, you have equation x plus 3 equals 5. You can solve that equation by subtracting 3, right, and you get 2. Or you can solve that equation graphically by graphing two functions and look for the intersection. So if you are looking at x plus 3 equals 5, the solution is algebraic, and you get the answer. Or the solution is going to be graphical, which will produce, right, the intersection of the two functions, function on the left, x plus 3, function on the right, 5. They intersect at 2, 5, x is 2. So, algebraic solution, graphical solution. Now, we spend a lot of time in mathematics learning about algebraic solutions to equations. Polynomial, quadratic formula, right? We learn about the all of these different methods for exponential and trigonometric equations, right? You know how to solve equations because equation says find value of x. And you go and you compute that. But then you run into equations where algebra fails. You run into an equation that says x plus 3 is equal to e to the x. You can just cry there. You can cry. There's no way to solve this using algebra. Because as soon as you free up one x, you bury the other one. You see that? If I put ln to free this x up, right, I buried the other one. So I get ln of x plus 3 equals x. And you say, oh, I need to free this one now. How do I free this one? Well, you put e, of course, right? So that kills your ln, but then you bury the other one. There is no way, comma, in hell, comma, to solve this algebraically. That's it. So how do you solve this? The only way is to draw the graph and look for intersection or employ numerical methods to find to whatever degree of precision you need. So algebra is not the ultimate answer to every problem. Therefore, this particular calculation here, which we would like to solve with 2.3, we can't. Because there is nothing, there's no sorcery of algebra that will help us with that. No factoring, no rationalizing, no, just nothing there. So that is in the simplest possible form, and then you can either do the graph or you can do the chart, and eventually something works. We are trying to avoid graphs and charts, graphs for difficulties of graphing, and charts for annoyance of computation, right? You have to compute number of points and then just sit there and just mind-numbing thing, like 15 minutes. We would like to have answers faster, so algebra provides us with those things. But sometimes algebra fails to provide those answers because it doesn't work. and then you have to resort to the methods that are taking more time, more energy, but that's the only way. So that's technically it. All right. Let's see what they have here. They say problem 26 looks awesome. I know you're going to love this. Leave your thank you notes in my mailbox. Limit t goes to 5. 4t squared minus 100 divided by t minus 5. Have fun. Did I mention that the final exam is in 13 classes from now? All right.
Technically, no. I believe
12.
you mentioned 14 classes from now.
That was last time.
Yeah.
Yeah. What do we have as the answer? 40. 4D. 40. Okay.
I got 4 or -5.
Answer, it's like Highlanders. There can be only one.
So one of them, right?
I don't know. There are no X's here. I'm trying really hard, but this air conditioning here is overpowering you. So employ breakfast now. Let's hear that voice.
Yeah, so x equals ±5, right? The numerator and the denominator is 0. For if you factor it.
We are definitely going to factor. I was asking for the final answer. I haven't heard the answer yet. Correct answer. Or actually I did. Or partially correct. I don't know. Let's see. So where do we begin?
Factor out the 4.
We factor out 4, and if you remember the rule we learned, you can actually kick that in front of the limit. It can go all the way in front of the limit because of the limit law that says that the constants can be kicked out all the way in front of the limit. Right there. So we can kick the 4 out. Nice. We are left with t squared minus 25, so that's t minus 5, t plus 5. T minus 5, these guys cancel, and what we get is 4 times 10, which is 40. Nice. All right, it is 40.
How do you get a 10? Like I got the 40, but like how do you get the 10?
All right, let's try.
Never mind. Yeah,
I was about to draw 5 stars and another 5 stars. Because right, we have 5 stars over here and another 5 stars over there, and when you add them, you get 10 stars. We can also use fingers. You know, right? Now, 11, right? 1, 2, 3, 4, 5, 10, 9, 8, 7, 6, 6 and 5, 11. Easy. All right. Yeah. Now, the question was clear. Find the limit at 5. And your answer is 40. Do we have a vertical asymptote at 5? No. No VA at x equals 5. No. Now, I can extend this question and say, okay, no vertical asymptote at 5. Is there another location, possibly, where we have vertical asymptote? In which case, you have to look at the function. This is where your pre-calculus thingy will kick in, and you will say, well, let me just get the list of all candidates by setting denominator to 0. Denominator equal to 0 produces only 5, and we already proved that 5 is not the vertical asymptote, so no. 5 was the only candidate, and it failed to be the vertical asymptote, therefore, no more. We're done. This problem is over, and we are moving on to, let's say, 30, and we're done with the section. It says location of vertical asymptotes, analyze the following function, and that's it. They give you more info, but I'm not, because I'm not as nice. So here we go. X to the fourth minus 49 x squared. They want you to so find all VAs. Now this would be the standard exam question. Maybe you want to star this one twice. I give you the function and I just say get the asymptotes. Now obviously it will include vertical, horizontal, and slant asymptotes. Since we only covered vertical, you're only worrying about vertical now. But there are other two kinds as well. So do we have any asymptotes? Two asymptotes? How many candidates do we have? 2 candidates and then 2 asymptotes? 2 candidates, 1 asymptote? 2 candidates, 2. I guess we'll have to go outside, take it outside. See,
I got 2 candidates for 1 asymptote.
Aha, you agree with the one of the states, right? Good. Let's see if we can resolve this in a civilized manner by employing the rules of calculus.
Yeah, I like the 2 too. 2 candidates, 2 asymptotes.
Yeah. Well, let's start by getting the candidates first by setting denominator equal to 0. So we have, come on, pen. I think the pen decided to take a break. I ran out of ink. X to the 4th minus 49x squared equals to 0. Factor out x squared, and then x plus 7x minus 7 equals 0. We have 3 candidates for asymptote looking here. X equals 0, x equals negative 7, x equals positive 7. So definitely 3 candidates. Now, when you do enough of these problems, you will see that this factor and that factor cancel, which means that's the one that it's not producing asymptote, the others will. But then that's the, self-discovery that you guys get when you do enough problems.
So we wouldn't consider that one. We would consider that one a candidate, even though
it's a candidate, but it's not an asymptote, right? You have candidates that go into a pool and they don't get selected, right? So that's what a candidate is. It's not a winner. These guys will be winners, and that one is going to be loser. All together, all 3 are candidates. So we start with the limit of x plus 7 over x to the 4 minus 49x squared. As x goes to 0, let's say plus. We know that this is the factor of the denominator. It will cancel x plus 7. So we have limit x plus 7 over x squared, x plus 7, x minus 7. These guys die off. And we are left with the denominator. So we're left with the limit x goes 0 plus of 1 over x squared, x minus 7. Now what we are getting is 1 over 0. You will quickly learn that when you have 1 over 0, it goes to infinity. And that should make sense because of the way division works. If you divide one paper into 2 parts, you get 2 parts. If you divide one paper into 3 parts, you get 3 parts, right? So you see that the bigger the denominator, the more parts you get, right? But the size of those parts is smaller and smaller and smaller. So if I divide by 0, I will get infinity on the other end. That's why we can't divide by 0, because you never get infinities. Anyway, so I need to put this in quotation marks because this is not mathematically sound statement, but that's actually what happens in practice. So this is going to end up being infinity. We were looking at the one-sided limit. We got the infinity, so that by the theorem we had states that there is a vertical asymptote at x equals 0. The next, yes? To be honest with you, it's irrelevant because of the definition. Either one would work. As soon as you get 1 over 0, 3 over 0, 10 over 0, it's going to be one of the two infinities. We actually don't care which one it is, and in some sense, they are the same thing. So we distinguish on a 2D graph, right, where it goes up or goes down to put negative or positive infinity, but also there is a notion in which they are one and the same. So, yeah, that's it. The next order of business is to take a look at the next value, which is -7. So limit x plus 7 over x squared, x plus 7, x minus 7. As x goes to -7, let's say from the left, these guys cancel, and what you get is 1 over 49 times -14. That's not infinity. I don't care how much it is. It's not infinity, so no VA. It's very simple. I really don't care about the value at all. And then limit x goes to 7 minus, let's say again from the left, x plus 7 over x squared, x plus 7, x minus 7. These guys cancel, and we again get 1 over 0, which shoots to infinity. So we have another vertical asymptote at x equals -7. So 3 candidates and 2 vertical, positive 7, yes, thank you. So we have 3 candidates and 2 vertical asymptotes in this case. Cool?
Does it matter if you plug it into the secondary equation we get or the original?
Well, this is original equation where this x plus 7 always cancels. You always start with the original equation, see what cancels, and then plug in the remainder. If you get a situation where it's 1 over 0 or 7 over 0 or 10 over 0, that's going to shoot to infinity. We have vertical asymptote. If you get a finite value, not over 0, then that means no vertical asymptote because it didn't get to be infinite limit. And just to connect all of these concepts now, guys, observe that the vertical asymptote always pushes the function to infinity, which is why we call it infinite limits, right? Whether it's positive infinity, negative infinity, this is where positive infinity goes, this is where negative infinity goes. So we call it infinite limits because the answer, the limit, is infinite. Infinite limits, right? Limit is infinite. And that's it. So I'll take a short break and then 2.5. Ciao.